In this video, we're going to continue our discussion of analysis of control flow graphs by focusing on what is undoubtedly the most interesting aspect of the whole problem, the analysis of loops. Here's an example control flow graph with a loop in it, and it turns out that the need for the special element bottom in our analysis is intimately tied to the analysis of loops. And so let's just think about how we would do our constant propagation example analysis with this particular control flow graph. All right, so what do we know about x? Okay, so initially we don't know anything, so before we enter the control flow graph, its value is top. And after the assignment to 3, we'll know that x has the value 3. The conditional branch here, the predicate won't affect the value of x, so it'll be 3 on both branches. The assignment to y won't affect it, so it'll be 3 here as well. And now we come here, okay, and let's focus on this statement right here. So the rule is that the analysis of x at y equals 0, okay, so with a value of x right here before the assignment to y, is a function of all the predecessors. So we need to know what the value of x is on both of the incoming edges, okay? Well, we don't have a value down here yet, so the question is, what is the value of x here on this edge? And in order to figure that out, we'd have to look at its predecessors. Okay, well, what are its predecessors? Well, there's this point here after the predicate. There's this point here between the two statements. And then there's this point here after the execution of y. We're just following the edges backwards here, looking at where we need to know information for x. So we need to know it here, we need to know it here, and we need to know it here. All right, and then because of this edge, that means we again need to know it at both of the predecessors of y equals to 0. And so now we're in the loop, and this isn't too surprising. I mean, if information about x depends on the predecessors of a statement, and you do follow that recursively, then you're going to wind up going around loops like this. And there's no good way, at least there's no particularly immediately obvious way to solve this problem. So how do we get information about the predecessors of y equals 0 when they depend on themselves? So to be more precise, looking at that particular statement again, in order to compute whether x is constant at the point right before the statement y equals 0, we need to know whether x is constant at the two predecessors, and that information depends on its predecessors, which include y equals to 0. Okay, so this is the conundrum. So how are we to solve this recursive problem? And there's a standard solution that is actually used in many areas of mathematics, not just in the analysis of loops, when you have these kinds of recurrence relationships or recursive equations. And the standard solution is to break the cycle by starting with some initial guess. So you have some initial approximation that is really not perhaps even expected to be the final result, but allows you to get going. So what we're going to do is that because of the cycles, all the program points have to have values at all times. And so we're going to assign an initial value, and that is what bottom is for. And the initial value bottom means, so far as we know, control never reaches this point. Remember this, we said this quite a while ago, several videos ago. And this will allow us to make progress. And to see that, let's go ahead and analyze this control flow graph now, where we assume that at all points initially, x has a value bottom, except at the entry point. So the entry point is special. Here we assume that we don't know anything about x because we know the control reaches the initial point. But initially, we're going to just say, well, x is bottom everywhere else. Okay, so let's equal the bottom there. The bottom there. Okay, I'm just going to fill in all the values. And I'm just writing it everywhere here. And there's really another one right here after the merge of these two paths. So we'll indicate that. All right, so there, now we have our initial setup. And now remember what the procedure is. We go and look where the information is inconsistent, and we update it. So where's the place where the information is inconsistent? Well, clearly it's not correct here. all right, because we know that after, if control reaches the point before x equals 3, then after the assignment, x will be equal to 3. Again, the predicate will not change the value of x, so we have to update the results on the two branches after the predicate. And after this assignment that doesn't affect x, to make that information consistent, we have that. Now, let's come back to our interesting case. Here, we know that x is equal to 3 on this branch coming into y equals 0. And so far as we know, control never reaches the other predecessor. So we're going to start out by assuming that path is never taken. And if that path is never taken, then it won't contribute anything. And so at this point in the program, we will know that x is equal to 3. So assuming that all this information is correct, we will be able to conclude that x is equal to 3 at this point. And notice how we've been able to break the cycle here and get started. So we just assume that this last edge in the cycle never executes, and if that's not correct, we'll find out later, and this value down here will become something other than bottom, and then we'll update the assignment again. All right, so let's continue on. So we have x is equal to 3 before y is assigned 0, so the assignment to y will not affect the value of x, so make the information afterwards consistent. We'll have to make x equal to 3 there. Now we have a merge of two paths. Okay, so at this point here, before the execution of this assignment, we will also know that x is equal to 3. The assignment to A will not affect x. We'll update that point there. And the predicate will not affect the value of x, so we'll know that x is equal to 3 on this back edge. And now this information has changed. Now, we now know that control can reach this edge because we followed a control path all the way to here. We have some new information about x, and so now we have to double check that everything is still okay. So here we have x is equal to 3 on this edge, x is equal to 3 on this edge, and our previous conclusion was that x was equal to 3 on entry to the statement y equals 0. Well, that's all still consistent. There are no places left in the control flow graph that are inconsistent, so all the information is consistent with all the rules, and so we're done. And this is the final analysis. We're able to conclude that at all of these points here, like say every point except the entry point, that x is in fact the constant 3.